Thank you for joining our today's session on preparing your application, preparing your files for application release. If you have any difficulties in with audio, or if you have any difficulties in understanding the concept, please type your questions in the chat so that we will try to cover the issues during the session. And this session is a recording. We will be soon sharing the recordings with all your attendees as well as the people who are registered for the same. And now let us get started. Yes, today we are going to review the basic fabrication process for a PCB, and then I will discuss some of the key aspects of PCB designing that are important to the fabrication process. And I will follow that with a review of key rules and constraints for PCBs that can be influenced and enforced by the designer during the design process. Then I will discuss how to avoid pitfalls. Finally, I will be providing a demonstration. We will wrap up with some closing comments and answering the questions from the chat. Let us now discuss about the basic elements of the PCB designing. In order to understand which basic elements from a PCB design, it is useful to review the technology of production, and I will not detail the specific process, but just briefly discuss the basic steps while remaining at a high level of abstraction. It all starts with the base material from which the board stack is formed. Next one, the key steps is drilling of the holes, which will become vias through hole pads and mounting holes. After plating of the hole walls. This metallization will also bind the layers of the fabrication board together. Along with the drilling, the most important step is trace realization. This is accomplished by etching the copper in an acid process. This step forms tracks and space between them. After hole drilling, plating, and trace etching, solder mask is applied to the outer surface. This is necessary to ensure that the component on the PCB can be soldered together reliably. The final step for any PCB is to make non-painted holes, cutouts, and outlines. I have deliberately counted a number of steps in the PCB production process and have highlighted only those that are important to this webinar context. Please do not take this information in this slide literally as a instructional material on PCB manufacturing technology. As PCB designers, we have a direct influence on the future appearance of the board and the resulting product. We influence technology choice, fabricator preferences, and we are responsible for the way these primary elements will be designed. The design is not only impacted by technical specification requirements for the end product, such as electrical, mechanical, and performance, but also by the requirements for bareboard product fabrication. Product development is a compromise between customer requirements and manufacturing requirements, both of which of course have an influence on the cost, profit, margin, and other business aspects of the end product. Let us discuss about what's important for PCB manufacturer. Let us have a look. First, the data must be provided to the manufacturer in an accessible format. Otherwise, you risk getting errors in the data or the project being rejected. Someone sends the design of the board as a source file. This method has some disadvantages. We recommend using specialized formats such as Gerber. Second, the technology requirements of design should not exceed the current capabilities of the manufacturer. If this happens, you are likely to have three options: redesigning the project with relaxed standards, which is not always possible; paying high production cost because the fabricator only has to produce a board outside of their normal process or such and the supplier. The most ideal scenario is when you know in advance the fabrication house that they will produce a board and the technical requirements of the design is within the known capabilities of the fabricator. This is the best scenario. Third, don't forget about materials. If you have special requirements, it's best to choose materials that are commonly available from the fabricator. Otherwise, you can expect delays, higher production cost, or potential redesign, or you can search for another supplier that may have materials available. Now let us talk about the what kind of constraints that can impact the design. Every PCB designer faces the constraint listed on this slide. First of all, minimum width of a conductor and the minimum clearance between the design elements in the figure. They are indicated by the letter W and C. The minimum diameter of the plated hole is indicated by letter D. The angular ring of the plated hole is the letter A. Clearance from designs elements to edge of the board or a cutout enclosed within a contour is indicated by letter D. Clearance from the copper to non-plated hole is indicated by letter H. The size of the solder mask opening as well as minimum width of the mask bridge between two adjacent openings is O and S respectively in the figure. All these limitations come from current capabilities of the bareboard fabricator and neglecting them cause problems. How we can avoid difficulties? Here are the simple few rules to follow. First, be aware of the technical capabilities of your chosen board fabricator. And as I have already mentioned, monitor and keep in mind the typical constraints if possible. Do not violate them. The second consideration is when using CAD to design boards, you must make a full use of the built-in design rules and constraint checking capabilities. The third is that all constraints which actual values must be described in the design rules and must be applied to verify that to the PCB design is correct. And finally, a full design for manufacturing checks DFM should always be performed before releasing the Gerber files. Now let us move on to the Ultimeasure and review the basic types of checks and methods available for you to use in order to avoid the problems with sourcing boards from your fabricator. Let us jump into the demonstration how we can avoid uh, all these fabricated issues with the help of the alternatives and how we can check all these design rules inside the Altium. We will just have a look with the alternatives. Now, what are checks we must do before releasing? We have made a list. There are 10 checks starting from width constraint, clearance checks, hole size checks, and number and types of holes, minimum ring verification, clearance between holes, clearance from the copper to hole walls, solder mass verification, clearance to outline, clearance from seal screen to exposed copper. These are the 10 checks we need to perform before releasing your Gerber to the fabricator. Now, let us verify all these things inside the Altin Designer. Yes, for this example, I have taken an example PCB, which is will come with along with the Altium 365 example files. Today I am taking this example file to do the 10 checks we need to perform when you are doing the generating the data files. Now we are in the top layer. If you can see, we have a bottom layer here. The first thing we need to check is if we have any unused pad or VR shapes are available in the design. We must remove that first before releasing the Gerber. To remove those things, you can see we have already few VR shapes which are unused already removed. Now I'll showcase you how we can remove the pad and unused VR shapes which are not used in other layers. How we can remove automatically that of the alternate. Let us see. For that, go to tools. Just here, option are remove unused and pad and VR shapes. From here, you can choose what's the type of action you want to perform. Either you want to perform VRs or whether you want to perform pads or whether you want to perform both. From here, you can check and you can able to select this option and click OK so that it will remove the pad and VR shapes which are not used in the other layers. Okay, this is the one check we need to perform. And the second one, we are going to discuss about the polygon pouring, because visually we will pour the polygon and we'll be doing, to do some rework again. What we will do, we'll shell the polygon and again we do rework. And due to in a hurry to release the design, we forgot to report the polygon which is shelled. This will create a problem after fabricating. In this case, how we can check the shelved polygons inside the RTM. We have a design rule is available to check all these errors. To access that, we have to go to Tools, Design Rule Check, and from here you can able to see what are rules to be checked. Here we have got two options: online and batch. I think online, the name itself suggests it will be checking the rules on the go. Batch means if you have based on the priority, it will be checking all the rules together. Okay, you have got electrical, routing, assembly, and if you go to the rules to check, you can see we have got all the rules here. We have enabled batch to perform the batch. Okay. Now let us uh, see how we can run this one individually, the design rules instead of batch. Suppose you want to run a specific design rule to see are there any errors. For running that in RTM, we have a PCB rules and violations panel available. You can access the same from panels and go to the PCB rules and violations panel. If you go to the PCB rules and violations panel, what are design rules we have available in the rules are able to see from here, and we can able to run each rule individually, or if you want to run all the rules together, we can able to perform DRC for the all the rules. First, let us check about the modified polygon rule. If you double click on this rule, you can see the design rule open. If you want to allow shell or allow modified, if you enable this option, the tool won't check the error. Make sure it is unchecked. Okay. Then let us see how we have any shelved polygons or any polygons are modified which are not report. We just see inside this design. For running this rule, just right click on this rule and then click on run DRC. You can see usually in RTM when you have any error, you can see the the text with the red. It will be displaying. See here we have got a plenty of errors listed. Basically on bottom, top, it is saying there's polygon is shelved and it's need to be report. You can see here. Okay, on the top layer. Okay, on the layer 5, there are a lot of polygons are shelved or few are modified and need to be report. Okay, this will create a huge problem if you send the Gerber without checking this one to your fabricator. Now, how we can overcome this issue? To overcome this issue, just go to Tools, Polygon Pose, just restore all polygons, and then again go to Tools, Polygon Pose, just say report all. When you say report all based on the design rules, what you said, it will be taking into consideration and it will be doing the reporting of the polygon. Now you can see here we have 0 violations. To make sure we our polygons are properly code and without any we don't have any shell polygons to cross check it, just again rerun this design rule so that we'll get a 0 violation. That means we have all the polygons are up to date and all report well. Okay, this is how you can have to check the unpolygon shell polygons or any polygons are modified or not at code. We can able to catch those kind of violations with this PCB rules and violations from this panel. Okay, now let us discuss about the 10 checks we need to perform before releasing your fabrication Gerber to the fabricator. First one is we will check the width constraint, which is very important, which will play a very key role where it will help you to connect the one connector to the other connector. Now, first we'll just start with running, the rule for the width constraint. Let's search for width constraint. Then you can see here we have this is the rule we have. The preferred width is, if you double click here, you can able to see we have got different criteria of width rules have been given for minimum 0.1 preferred 0.125 and maximum width 1 mm for top layer. In RTM, we have a flexibility to have a different width rules for different layers. These are criteria we have set. And now let us see, are there any violations we have with respect to the width. Now let us run the same violation. Now I click on this and say run DRC. Now you can see here we have a few violations has been found in the bottom layer, and you can see here the based on the origin it will display the what is the location. We have origin in the middle. That's the reason it is showing we have got some negative values, and it's saying is bottom active width is 0.09 and target width is 0.1. You can see this is the trace where it been routed with if you want to see the violation, just select that in RTM. If we have any violation, it will display with red color with a cross symbol. Just select that violation and then press shift plus B. It will open the properties, the board inside, so that if we expand it, you can be able to see what is the issue. And if you double click properties, you can see what is the violation. You can be able to see if you want to wave it, you can wave it or go to width. You can be able to control from here. Yes, we have only issue with the only one trace. Like it's not required to change the rule. Now let us change the value of the trace. Let us select one segment and press tab to automatically get selected when you press tab inside the RTF. It is difficult you to reroute it. Why? Because this is a huge trace and it's been completed. Then how we can uh, take this one to the right with, okay, as per the design rule. Just select the trace. In RTM we have option for retrace selected. Just go to root and click on retrace selected. If you click on retrace selected, if you go to the properties of the trace, it is of width 0.125 still. Okay, let me root retrace. I'll just have to make now. Let us again rerun it. Okay, this been changed to 0.1. Okay, if you see here the properties 0.1. Okay, like this you can able to perform the bit constraint rule. And if you found any error, if you want to bring that to the latest tool, just select the trace and hit tab to open the properties and then go to root retrace selected. If after routing, if you change the value of the trace, if you want to bring that to the latest design tool, just select the trace and say retrace selected. Okay. Or else you can also perform the same from PCB by using this nets option. You can able to pick the appropriate net and just select it by enabling the option and use this option to get it to the latest width. Okay. This how you can able to check this width rule. And also, if you want to check with the Polygon for if you have any islands which you don't require, you want to follow the trace with criteria. Here you can see we have got islands we have mentioned at 0.127, which is a required criteria. But we in our case we have design rules starting from 0.1 to 0.125 preferred and 1 mm. And if you want to have a preferred value of 0.1, maybe you can able to use the specific value here as a minimum 0.1, and then you can able to do the repouring. It will follow the see the minimum criteria where it can able to remove the polygon necks which are less than 0.1. Like this, you can able to use this polygon what neck option you can able to control as per your width requirement. Okay, and the second check we need to perform is for the clearance verification. Okay, let us perform the check for the clearance. The same clearance rule you can able to check it from here. But if you are unable to find the rule where it is, just select anything and press the starting letter. You can able to see what it is. If you look at the clearance, we have got multiple clearance rules are available, almost 16 for the between all differential pairs, and we have got rule for the NPTs. That means this one. We have different rules available if you want to run for a specific rule, like is suppose I want to perform then for this particular criteria, just right click on this and run DRC for this minimum clearance rule 0.1. And here you can see we have got 21 violations as it is saying there are for some collisions. If you double click on this, it will highlight what is it happening here. It is saying some collision between the track between the track which is of 0.1 less than 0.1 mm. If you look at this particular component, this is a net tie. I think you are aware of the net tie. Your net tie will be used to connect two different nets. That's the reason it's flagging error. All these errors, what is flagged are related to the net ties. So that if you want to ignore, you can ignore it, or you can able to right click on this. You can select this all these errors and right click and click on waive selection violation and just click OK. Okay, you can see now this issue is being waived off. Okay, or you can like this you can able to waive these violations which is not required. Okay, to check. Okay, and also we have got other rules as well. You can able to check those other rules and you can able to perform the same. Okay, and if you want to run for the polygon clearance for the layer 5, just check this one and just run this error whether we have any issues in the polygon in the layer 5. Or if you want to do any modifications for the particular rules, just go to design and from here you know to pick them. Suppose say here we need to have a more clearance rule to be applied for the polygon uh, for the copper to copper, let us say for the polygons. You can see here this one. Here we have see here mentioned the copper to copper, let us say advanced. Here the polygon to just polygon to polygon. You want to give more clearance. Just this uh, change it to a different value if as per requirements. Because I want polygon to polygon, the clearance should be followed 0.15. Let us say apply and OK, and then I click on this and run DRC so that it will tag if you have any issues with the polygon. Still, it is showing the issues with the collisions only. I think we don't have any issues with the polygon force within the range of that 0.015 mm. As I told, we have already waived off. Then no need to worry about this one. Okay, if you want to check all these two together, just right click on the screen and constraint and say run design tool check. If you get any errors, you can just spend a good amount of time and try to resolve these errors. And this all these errors are related to the potential point. Okay. And the next check we need to do it is for the whole size checks. Okay, what is the hole you required for fabrication? What is the hole size you are used in the design? We need to verify. For that, let us make it is clear. Let us go back to the normal mode. The next check we are going to check is for the hole size checks. For that, we need to go to the inside the design rules. For that, go to design rules. It will be there under manufacturing, and it will be there under hole size. See here, we have here the hole size minimum. We have given 0.2 and the maximum is 6 mm. And if you run these rules inside the PCB rules and violations panel, if you should not get any errors. Um, then search for that rule is an old size constraint. It is the value. Here also can have to access the same. Just right click on this rule and just say run design rule check. See here we have used the whole size as per the design rule. That's why I don't have any design rules here. Okay, this is the third check. And the fourth check we need to perform is verify the number and the types of the holes. What types we have and what is the count of the holes we have, we need to verify. This is the fourth check. To verify the number of holes and hole sizes, we need to go to panels and say PCB. And then from the drop down, we have to choose the option called hole size editor. And if you can see here, what the holes we have a hole of 0. Hole size of 0.5 mm, hole length of 0.85. It is slot, and you can see how many of you have plated and the symbol. If you click on this one, it will automatically get highlighted. What is it one based on this selection, normal or mask or dim, and based on selection, it will highlight the particular hole on the design. Here you can see we have got both hole size of 2 times 0.6 and 6 mm. But here in case we have got the whole length of 1.9 and it is of 1.11 mm. If you're trying to match both the same whole length so that you can reduce the fabrication cost in this regard. Okay, and also we have got 0.85 a whole of two numbers, and sorry, I just make it pin. Okay, and here you can see symbol for the each hole based on their hole size. Okay, and you can see we have got 1240 0.2 mm of hole size. They are the via count, and these are via hole size, and we have got 366 VS of dia 0.3 mm. Okay, and total we can able to see what all we have been able to easily get the total count of your pads and vias in the design. If we have any 0.8 mm or 0.9 mm hole sizes we have used, so that we can able to make it either 0.8 or 0.9, so that you can optimize and you could save the time during the fabrication. Okay, and also it will also give you some kind of reduction in that cost. Okay, this is how we can able to do the and verifying the number of holes types inside the RTM designer. The next check we need to perform is the minimum annular ring verification. Okay. Okay. Now to verify the minimal annular ring, now let us take a via. This is a via. You can see this is the hole and this is the annular ring. If you look at the properties of this one here, it is mentioned the dia. It is 0.4 and it is 0.2. And what is the annular ring we have? Just verify. Just Control M and then just measure what is the annular ring we have. It is around 0.101 mm is the annular ring. It is available. Okay. Now let us see what we have set inside in the design rule. What is the annular ring requirement? Let us go to the PCB rules and violations, and I can see here we have an option for minimum annular ring requirement. Right click and go to properties. Here we are set it as a 0.1 mm only. Let us see, are there any deviations at more than 0.1 mm or any annular rings of vias are less than 0.1 mm we have, we will just run with a DRC. We'll check with a DRC. Right click on this and just perform run design rule check. And here we have a issue where we have the few vias where the annular ring has been used less than 0.009 mm. Here we have got two suggestions. One suggestion is let us select this all these vias and make it the appropriate size, increase the diameter to just get that 0.1. Let us see whether I have made this via as 0.5. Let us see whether I got still it is 0.99. Let us make maybe 0.55. Okay, I just control M. We just measure it. Just control. Yes. Now we got it around 0.131. Yes, this is giving the. I just giving an example. Let's not do like that. Like simple. Just how we can able to change these values. I think we have got only violation for the few vias where you can able to. I think all these vias which are here will got the same issue. Now let us select this and find similar objects, and here we like to select only the via dia of 0.48 mm because rest all are within the range of 0.1. I want to increase the core, the via dia so that I can able to achieve the required annular ring size. That's why I'm just using what and all matching this 0.48 mm to get selected, and then click apply and get OK. See here what and all we have uh, selected with a value of 0.48 only got selected. Now make it as 0.55. Just enter. Okay, and go to this option here, and again rerun the design rule. Whether see we have any violations after changing the via annular link, whether you have achieved that particular value or not. Okay, like this you can change the values, and you can able to check this minimum handling requirements are meeting the design rules or not, and you can get that rule corrected. Okay, yes sir. This is all about the checking the minimum handling verification. Now that is the next check, the sixth one, verification of clearance between the pole walls. Okay, that means measuring the distance between the two pads which are close by and their distance. Let us locate a net name, differential pair editor. It is USB. I think this will be ideal. Yes. Yes. Okay, let us take this two into example. Now we need to verify what is the distance between these two hole. That means hole to hole gap. For that, just do Control M and select the distance between this hole to this hole. Here we have got the hole size of 0.3 mm. Now let us see whether it is meeting our design requirements or not. Let us have a check. Go to the same and hole to hole clearance constraint, which are very close by. Just click on this and then right click on this and right, double click to open the properties. Here we have mentioned the minimum hole to hole clearance should be 0.2, but here we have got a value of 0.3. Now let us see whether that will be flag an error or not. This okay. I click on this and say run design rule violation. Yes, we have got violations. You can see here for this hole-to-hole clearance constraint as we have placed two pads for this design. Um, which are getting collide. That's why it is throwing an error. We have got collision. And if you see the close look at this component, this is a micro SD connector where it need to have multiple pins. That is the reason it's been placed two pads like this. Uh, then we can maybe waive these two violations. It is as the requirement. Just view of this. Okay, now let us look at the other 8 violations. We have got um, here it is showing we have got some the clearance between these two is 0.2, which is less than 0.2. I think almost all are within the range of 0.2. Uh, here is also 0.2 because they are exactly as per 0.2. That's why it is saying it is a violation. If you make it a little bit smaller the value so that you can avoid it, or just slightly adjust the whole size of this where you have got the error to overcome that issues. Okay, let us do this one all okay. And once after doing these changes, let us need to report the polygon because we have polygons. Let us do the same report all, which is required, and then run this DRC. Still, we have few. Okay. Okay. Yes. See, now we don't have any errors. Okay. Like this, we need to perform this error verification and do the modification then and there to so that you can able to release your Gerber without any issues. Now, next check we are going to perform is number 7 is verifying the clearance from output to the whole walls. That means from the whole wall to the polygon port, what is the gap we have achieved inside the design. If you take a example of this slot, let us do the measurement. Let me make it is one of the control M, which is used to measure the distance. Reports measure distance from here to here. What is it? It is around 0.251 mm is the copper hole to polygon core will be the band distance here. Let us see how it will look. We need to look at the clearance constraint rule. Okay, further go to PCB tools and violations. Clearance constraint. We have a Yes, general rule for all. Just go to properties. Here we have got pole to poly, it is around 0.2. And what we have here, I forgot that value. Let me do it. It is also 0.25. What we have here is 0.2. Okay, pole to poly 0.2. Okay, if you run this, especially for uh, this one, just right click and run DRC. I think this, I think I have told this all are related to net type. And just see the value. Here is perhaps to net type. As we already discussed earlier, I think there is no issues with from the pole edge to the polygon. I think this error we have already discussed. This can be ignored. I think we don't have any errors for this one clearance from copper to the old ones. And the next rule we need to check is for the number 8 is for the solder mask verification. That means the solder mask opening the clearance between the components, and what is the opening required for the component pad, and what is the opening clearance between the two pads. You can able to see with the help of the design tools errors. Let us verify this. Typically, the solder mask is in green, but other colors also available. This solder mask ensures the components and elimination of the solder bridges, and also plays a role as general protector to the PCB. Okay. Uh, we control this solder mask with two rules. One is solder mask expansion, and one more is minimum solder mask silver. Okay, just go to the 2D mode, and if you select here, if you go down, you can see we have got two options. The solder mask expansion, where you can able to control it from rule or from the manual. Based on your recommendation, you have to select these options. Okay, now let us see if you have any errors. We will get, but this minimum solder mask level constraint. Now let us go to the minimum solder mask silver constraint rule. Here I have set the clearance between the solder mask openings should be 0.1 mm. Let us see if we have any violations we'll get inside this design. Let us right click on this and say run design tools for the minimum solder mask silver constraint. We have got almost 690, 659 violations. I can see here we have a violation between in footprint. It is saying 0.05 is the clearance, but it is 0.1 as per the design rule. And we have a few others. You can see 0.05. Most of them are 0.05. And one thing is we have 0.03. Now, how we can overcome this rule is by making the value lesser than the required. Then go to properties, then make it as 0.02 and OK, and run the design. Still, we have got two violations, but as here it is 0.02. As that actually there is no gap actually. Yes, it means the opening is very close because of the fine pitch of this IC. You can, if you want, you can wave off this and you can proceed further. Okay, this is how you can able to check the solid mask verification. And Ninth check we need to perform is clearance to the outline, the clearance from the outline of the board. That is make it board normal, and let us move to the top layer. Let us move to this layer. That means clearance from the board edge. If you can see here, uh, the board edge is this outline, and we have the polygon which is poured towards the board edge. If during the fabrication it may get open and it may get in touch with any metal object which is where your PCB get inserted, it may create a problem. We need to maintain a sufficient amount of clearance from the board edges. Okay, for that you have to set the design rule. For that, go to design rules. There is one design rule under manufacturing board outline clearance. Okay, just select this rule and right click, just a new rule. Here the minimum is we need to have 0.2 is our requirement to maintain from board edge 0.2. Okay, now just click apply and okay. Okay, and just see if they have any violations. Minimum board outline. Yes, board outline clearance. If you double click, you can see the properties of the board outline here. And to run this DRC, I click on this, say run design to check. See, we have got too many errors related to the board outline clearance. The top layer. Okay. Once the rules are applied, we need to do some Polygon report to work on this issue. Let us do that Polygon report. On. You can see here the polygon has been report and it's maintaining distance from 0.2 from the thing. Again, let us run it now. Still, we have issues with the other objects which are not in the signal layers. Maybe there are some thing on the yes, this is the thing. This is the issue we are getting with a non-elliptical object. Now we don't want to verify for the non-elliptical objects. Let us modify this rule. Say custom query, just on copper, just mention so that it only check for the copper traces, which are elliptical properties. Again, run this design to check. See, now we don't have any design violations as this violation is got due to the silk screen text which is on the near the board edge. Okay, this is how we can able to check the clearance from the board edge with respect to copper. The last tool, the 10th rule, we are going to check is clearance from silk screen to exposed copper. Your organization may have specified rules for silk screen. Silk screen can be used for assembly, debugging, service, documentation, etc. For fabrication, the silk screen should not cover open areas. We have two separate tools for the silk screen. If you go to the rules, switch to solder clearance, we have one rule, and we have other rule is switch to silk clearance. Okay, we have two rules, and we have set silk to silk clearance is 0, and silk to solder clearance is 0.1. Now let us run a rule for the silk to solder mask clearance. Let us say yes. Silk to solder mask clearance constraint. Let us run this. we have yes, we have got 12 violations, and we're saying some collisions are there. I think these texts are getting collided with each other. Let us move this so they get, and this there is one collision also happening. Yes, I think we change it. Let us again run. This time it will get reduced to 4. It is saying some 0 point. Okay, let us move this off. Okay, this time it will be 0. Let us unclick, run. Does I see rule check? Yes, we have 0 errors. Like this, we have to spend some time and clearing the errors. Okay. Yes, these are the 10 uh, uh, rules we need to check before releasing our Gerber into the ultimate designer. Once we check all these 10 design rules, now we can finally go to tools, design rule check, yes, run design rules, so that we can get others which are not verified by us. So the other rules also get verified, and it will give the detailed report. We can see still we have got some 13 violations, and 6 are waived violations we have got. And if you go to the 13, you can see we got clear constraint for differential pad 2 and 100 nets 4. There are 400 nets are available, and we have got some collisions happening, and we have some silver gap. We have got 2 issues. Okay, like this we can able to perform, and we have to make sure all these violations should be taken down to 0. Okay. Yes, this is all about the preparing your files for fabrication release. Now, we are open for the questions, and if anyone having any questions, please